You like it? Great.
Tutorial first?
I think we'll do tutorial first, yeah. Yeah. We start with balancing the equations, is it?
Yeah, it's chapter 2.
Which one? Is it supposed to be good? I still think the original one is the best one. The one that's like 20 years old now or something. There's probably, in which one? A little bit maybe. There is somebody that gets eaten alive by a T-Rex.
Yeah, I would like the toilet scene.
The toilet scene's a classic, isn't it? Classic. Movie classic. Yeah. Alright. Right, let's start with the balancing the equations. We'll do that homework first. That is a very strong dessert. I can still taste it in my mouth. Very strong. Okay. There we go. Does anyone have a copy of the questions? Whoopi, do you have the questions there I could look at?
No.
You don't?
Yeah.
I thought you always print them.
I forgot to bring that.
That's okay.
That paper.
I'll open it. Dropbox, DIFC, physics, atoms. Which homework do I need to do? The first one?
1 to 3.
I need to do 1, 2, 3? I didn't do any of them?
Yeah.
Okay. Okay. Right. Complete the following. Well, let's just I'll do the I think we'll just check our answers together because I don't think these were that hard, were they? So what did we get here? This one should be 92 and 239. Okay. And this one here, this one would be 29 and 62.
2.
Yes. This one here would have to be 11 and 24. All right. I don't need to do the rest of these. I mean, you all know how to add, don't you? So
How to? Yeah.
your elementary school teacher will be proud of you. What about this one? This undergoes 3 alpha decays. That one's a little bit more interesting. So this is 2, 2, 5, 89 AC. And this becomes something else with 3 alpha decays. So that would have to be 83. Yeah? And that would be 2, 1, 3. Yeah? Alright, so that's easy peasy as well. And then this one here. 2, 3, 2, 90 TH becomes 208. 82 pp, and then it's so many alphas, and then so many betas. Yeah. All right. So I think the easiest to do is to start at the top row, because this would be 208 plus 4x. So that means 24, 12, 6. This has to be a 6, because 6 times 4 is 24, and 24 plus 208 gives me the 232. Okay, so if 6 times 2 is 12, 12 plus 82 is 94. So this has to be a 4, because I need to minus 4 from it. Yeah, did you get that?
Yeah.
Alright, so do I Do I need to do
No,
this?
no,
I
no,
don't
no,
think
no,
so.
no, don't need to.
No. So do you see why I'm saying these are great for the exam, because these questions will be 3 or sometimes 4 marks. It's very good.
Yeah.
Like 3 or 4% for Adam. Really, it's pretty good.
Only need 1 minute.
Yeah,
Yeah.
yeah, it's very good. It's very good. So this one's not so difficult. Let's have a look at the next one though. Whoops. Yeah, okay. This one now. Right, I need to get the calculator probably, won't I? Okay. Who's texting me? Like them over. What have they got for me? Dear customer, blah blah blah. Okay. A radioactive sample has 10 to the 24 atoms and an activity of minus 10 to the 23 becquerels. What is the K constant? Alright, so this one we just need to use the formula
Gamma.
gamma?
Not gamma.
Not gamma.
The constant equal minus A over.
A equals, now don't say, what's the name of that letter? This one?
Gamma.
No,
Adam gamma.
not gamma.
That is
Yeah? Yeah?
constant.
True.
Decay constant.
It's true. And it's Greek letter?
What's that? Gamma. Not gamma.
Not gamma. It's not gamma. It's not gamma. What is
The
it?
wave function. What's that name?
Come on, we're all waiting.
Is it important?
Ah, it is. I think you should know its name. Yeah, it begins with an L. Would you like to tell him?
No.
L-A?
Lambda.
Yes, lambda, correct. A equals minus lambda L. So the A here is minus 10 to the 23, isn't it? Yeah. And minus lambda, and this is 10 to the 24. So lambda equals 0.1. Yeah? Per seconds, isn't the unit?
Yes.
Yeah. Okay. 1b. What is the activity after 10 seconds? Okay, so the activity after 10 seconds, we can get it from this formula. So that will be minus 10 to the 23 e minus 0.1 times 10. Can you type that in, please, and tell me what you get?
Minus.
You have it?
Yeah.
What did you get?
Minus 3.68 by 10 to the 22. Big. Becker.
I don't know how to say it, to be honest. So I just say BQ.
Becker?
Not baker, no. They make the bread. Right. How many atoms are there after 10 seconds? So I could use this formula,
N equal
n
N0.
equals n0 e minus lambda t. Or I could actually use this formula, a equals minus lambda n. So I'll use this one since it's a tiny bit easier, because I can then say n equals minus a over lambda, which in this case will be minus 3.68 times 10 to the 22 over 0.1. So that is 3.68 times 10 to the 23 isotopes, radioactive nuclei.
Change the word.
Change the moles? It will be about half a mole.
Yeah, 0.611.
Yeah. What is it as a mole?
0.611.
0.611 moles. You tell me. No, tell me, you can. Correct, yeah. Okay, 1D.
No.
Yeah, exactly, yeah. 1D. How long until you have n equals 10 to the 21. Okay, so now I have to use this formula. So I want 10 to the 21 equals 10 to the 24 e minus 0.1 t. Alright, so first I divide by 10 to the 24, so that's 0.001 equals e minus 0.1 t, isn't it? Yeah, that's right, isn't it? What should I do next? Log, cancel, and then next, divide by minus 0.1, cancel. So now I have my t is this, whatever this is. Can someone hit that in, or do you have it? Yeah.
Can you calculate log calculator? Is it possible?
Yes, but it will be a little bit difficult. Like for example, it's possible. It's possible, and in fact, the nearer the number is to 1, the more accurate your calculation will be. There is a way to calculate it, but it's only a approximation.
How does our calculator come up with that?
It uses something which isn't on this course, it's on the further maths course. But basically the calculator has a formula for log x that is basically something that would look like this. And it probably goes all the way up to maybe power 20 or something. But that's only an approximation. But there's actually other ways you can calculate it too. Like for example, you know that log x equals integrate 1 over x, correct? And you know that 1 over x looks like this graph, correct? And you know that integration represents area, correct? So you could change log x into a problem using the trapezoidal rule. So that was one way you could calculate it. And that's actually a common way to use a computer to calculate things like this. Okay, so what is this here?
69.16.
69.16.
1 second.
0.1
Yeah.
seconds. Okay, is this one okay? Yeah. A sample of sodium 24 has 10 grams. 7 hours later, it has 5 grams. So I think we can kind of see what's happening here. It starts with 10 grams and it goes down to 5 grams. So that actually tells us the half-life is 7 hours. Although when we did this lesson, we didn't do half-life yet. Sodium will decay by releasing a beta. What atom will it become afterwards? Okay, so how many protons in sodium?
11.
11. And it decays by releasing a beta. So whatever is left here, this has to be a 12. This is, no, it's not carbon. Carbon is 6, isn't it? Magnesium. Yeah, so the sodium turns into magnesium and releases a beta. Okay, that's okay. And maybe also a gamma of some kind, radiation ray. Multiply both sides by the molar mass and divide by Avogadro's number. What's the new equation? So basically, we did this one in class. You end up getting m equals m0 e minus lambda t. 2c, what is the value of the decay constant? Well, if we use this formula, we get 10 grams, 5 grams equals 10 grams e minus lambda 7 hours. That's 7 times 3,600. So I can solve this. That goes into that. The answer would be 0.5 equals e minus whatever 7 times 3,600 is. I do my log, I can cancel, and then I divide. So again, if you have the calculator handy, can you tell me what you get when you type this in? And that's my lambda.
2.75 by 10 to the minus 5 H.
Thank you. Right. 2D. How long until only 10% remain? So we go from 10 grams to 1 gram. So let's see, 1 gram equals 10 grams, E minus the lambda I just got times T. So again, we do our division, and we'll end up getting 0.1 equals E minus lambda T, and then we'll do our log and cancel, and then again divide by the minus lambda. So the answer will be whatever log of 0.1 over minus over minus 2.75 times 10 to the minus 5 is, let me see, hang on, 5, 2, 3, 7, 20, is it like about 22 hours?
Close.
What?
23 hour and 50 minutes.
23 hours and 15 minutes. Yeah. So basically a day. What do you mean how?
How do you calculate from just look at
Trinity College.
Let me. How? Give me a hint.
I remembered that the half-life was 7 hours, so to go from 10 to 1, that's 5, 2.5, 1.25, so it should be a little bit more than 3 half-lives. So 3 half-lives is 21 hours, so...
so you're not calculating.
No, but it looks like I did, so it's more impressive. Yeah. Okay. There's lots of little tricks like this, you know, lots of little tricks. Like, for example, if I said, I don't know, 65 squared, what's that? That would be 4225, you know. Or if I said, I don't know, like 55 squared, that would be 3025. Now, I'm not a genius. I know, for example, when a number ends in 5 and you square it, you always get a 25 at the back. And the number in the front, if you multiply it by its neighbour, 5 times 6, that's 30. 6 times 7, that's 42. You can test it, like pick a number, like 45 squared. So that's a 25 at the back, and what's 4 times 5? 20. Now check it out, 45 squared. What do you get? 2025. It's not genius.
Did you
Just
get
trick.
it like yourself or you got it online?
No, a student taught me this one.
Okay.
Yeah, and I'm like, ooh, that's a good one, I'll remember that now. Okay, is that the last one there?
Yep.
Yeah. Okay, next one, so. Right. Be careful, Rupi. Half-life. Here we go. Are you off the fasting now or not?
Finished.
Finished fasting? I didn't see you eat it. You're finished then? Right. The isotope radon-222 has a half-life of 2.8 days. Some radon has leaked out of the container into a physics lab, and it says 25 grams has leaked out. How long until less than 1 gram remains? And I want you to use half-life. Okay, so we start off with 25. After 1 half-life, we'll have 12.5, 6.25, 3.125, 1.5 something, and then less than 1. So about 5 half-lives is what you would need. It's 2.8 days, so that's 14 days. 2 weeks is the answer for the first one, 2 weeks.
Is it right?
I don't know, I just did this in my head, so it's
I
2...
thought you from
Oh, sorry. I said 5 half-lives,
yeah.
which is 14 days, which is 2 weeks.
You know the one is talking
Yeah, 5 times 2.8. Isn't that 14?
I got
Yeah, and 14 is 2 weeks. A fortnight. Yeah? And why are you confused? Is this right? What am I doing wrong? Is it okay? 5 half-lives.
No, not 5.
So not 5, what then?
I got 9.
9 half-lives. Hang on, let's check. 25 grams, what's one half-life? 12.5 grams.
Yeah.
Yes?
Yeah.
What's the next half-life?
6.25.
Next?
3 point something.
3 point something. Next?
1 point something.
1.5 something. Next?
That's longer.
Next one is less than 1.
What?
Well, hang on, if you're 1.5 something and you half it, then you're like 0.8.
Yeah.
So 5 half-lives.
1 gram is 0.01.
0.001.
0.001.
Yeah. No, don't. Wookie.
Why?
Look at me, look at me, look at me, look at me. 25 grams.
It makes sense. Yeah,
Okay,
you're
fine.
it makes sense. But why?
I don't know why. 5 half-lives, 2.8 days a half-life, so that's 14 days, so 2 weeks for the first one.
So we don't count the at the beginning,
Yeah, you don't, because 0 days, it starts at 25, and then after one half-life it goes to 12.5. So 2 weeks, a fortnight. Yep. I don't know what you did wrong, Mookie, I'm sorry. What is the decay constant? Okay, so I should use this formula. T a half equals lambda times log 2, isn't it? So then the lambda is the half-life over log 2, which is 2.8. Now, if you want to use, oh yeah, we'll use seconds.
Is the formula lambda log 2 over lambda?
Oh, is it? I got it wrong, sorry. Sorry. It's log 2 over lambda. So the lambda is log 2 over the half-life, which will be 0.69 over 2.8 times 24 times 3,600. So what do we get, please?
2.87 by 10 to the minus 6.
Yeah? What is the initial activity? So the activity at the beginning will be minus lambda n 0. Well, we know the lambda. How many atoms do we have at the beginning? Well, how many moles do we have? So the molar mass is what? 222 grams, and we have 25 grams. So what's that, like 0.1 about?
0 point something.
No, I obviously know that. So what is 25 grams divided by 222 grams?
Yeah.
What is that?
I don't know, but I use that and I buy. I multiply by negative.
0.113. 0.113 multiply Avogadro's number.
Yeah.
Right, so what did you get here?
Minus 1.95 by 10 to the 17.
17 BQ. D. How long until exactly 1 gram remains? Exactly. So we estimated 2 weeks. Let's calculate what it exactly is. So if I use my formula, 1 gram equals 25 grams, E minus lambda T, and we know the lambda from up here. So when we solve this, we end up getting T equals 0.001 divided by 0.025. 0.05 over minus 2.87 times 10 to the minus 6 log of this number. What's that, please?
That wasn't my problem. I used 0.25.
That's a big problem then.
Yeah. Let's see. 0.001, 0.025. Right?
Yeah. Should be a big number.
Yeah. 1121559.
Thank you. 12.98 days. So roughly 13 days.
Do you have to change it to this?
If the question doesn't say, then you don't. But if you did, you know, still either way it's the full mark, as long as they don't specify a unit. If the room is 20 by 30 by 3, then what's the density when there's 1 gram present? So the density of radon in the room would be mass divided by volume. What did I say the volume was? 20 by 30 by 3?
Yep.
So this should be very small. What do we get here?
5.56 by 10 to the minus 7.
Minus 7 kilograms per meter cubed.
Yeah.
And finally, what is the molarity of radon in the room? That is moles per liter. So, how many liters do we have? Well, the volume is 20 by 30 by 3, but that's not the volume in liters. Does anybody know how many liters in a meter cubed?
1,000.
1,000.
Yeah.
So I need to multiply my volume by 1,000 to change it into how many liters I have. Okay? So if you have 1 meter cubed, you have 1,000 liters.
Yep.
If you have 1,800 meter cubed or whatever, 1800, then you multiply by 1,000. And likewise, we don't use, for molarity, we don't use mass on the top. We use moles. Now, 1 gram is not much of a mole, because I think I said a mole is 222 grams. So 1 gram would only be this many moles. So the molarity should be very small, moles per liter. What do we get here?
2.5 by 10 to the minus 9.
And what unit do you use for moles per liter?
Yeah.
Now what's the unit in chemistry, moles per liter?
Yeah. Same.
Capital M,
Yeah.
moles per liter, molarity.
Yeah.
Yeah. That's a chemistry question I threw in at the end. You did this in chemistry, like probably semester 1.
Yeah.
Yeah. Okay, is this one okay? Yeah? Okay. Do you see why I say that the atom question is a good question in the exam? There's nothing too difficult about it. It's kind of a nice exam question. Yes?
What is the later lesson? Are they hard?
This one is just graphs, like what we did in the capacitors, you know, using log. This one is a picture lesson.
Just picture?
Yeah.
The popular.
Pictures. This one here is Einstein's famous equation. This one here is nuclear power plants. This one's theory. Yeah, this one's like calculation, theory, calculation, theory, calculation, calculation. Yeah? What? What's wrong? Did you like this lesson?
Yeah.
And this one?
Yeah.
And this one?
Yeah.
And you probably like this one? Yeah, so everything's great.
Yeah, but then there's like application.
It's only pretty pictures. That's all we're looking at.
Yeah, but then if you're doing exam, you're not gonna draw any those pretty pictures.
No, they'll ask you to write a sentence.
Not
Why do you hate writing so much? Maybe this explains your grade.